We are recording.
Very good. Well, welcome everyone to our education session for today, June 30th. Thomas, so I know the other day you had mentioned you had some ideas for today's discussion. Is that right?
Yeah. I'm also having a whiteboard where I can sketch something.
Oh, tremendous.
Yeah. I connected with my laptop, so.
Okay.
Yeah. So I wanted to talk about monoids and what is closely related what Greg's explains in Casper session. So yeah, this is okay. I will first share screen here.
Okay.
So Greg mentioned monoid on the Casper stand-up. How can I make this bigger? Oh, it's not bigger. So here, this structure, right? This is the same thing as he explained in monadic design pattern, monadic design patterns from the web. And here's this monoid structure, and this is like a very simple structure. So I want to show different instances that we already know and relate this to Rholang or lambda calculus. So now I will switch to my whiteboard. I hope this will work, and I hope I will succeed to to write what I have in mind. So I have two whiteboards which I found out because I want to show different views. So here. So if we have just simple objects, right? For example, we can have just boxes. And they have something that connects these boxes, right? We can see this is like a sequence, right? So in these spaces between, we can imagine that there is some kind of connection between, some kind of dot, right? And now the question is, what kind of structure we can imagine? What kind of different structure we can imagine if we are thinking about what can be a box or what can be this dot that is connected. So examples of this kind of structure can be, for example, some kind of just characters, right? And so what is in between these characters? What can we imagine this operation can be in between these characters? For example, we can say this is a string, Greg mentioned as one instance of monoid as a string. So we can say that the boxes are the letters, and the connection in between. So what can be connection in between when we are working with strings?
Functors.
For example, if we have this string ABCD and maybe another string EFG.
Concaténation.
Yeah, exactly. We can just how this works?
Or join or concat.
Yeah, join or concatenation. So what is the type of concatenation?
Right?
Concatenation function. What will be the type?
Function with two parameters that return. The two are strings, and it returns a string.
Yeah, exactly. So I want to move this. I think that I cannot move just this part. Okay. ABCD, EFG. So what happened here is it's difficult to erase something. So as Rafael said, we have this kind of operation. Something as this box. This is the first parameter. We have some another parameter, and we are returning a box. Right. So this means that basically we have a function with two parameters which will like return the same type as we have for these parameters. For example, we can have another example which is very similar. Sorry for that. I can make it smaller. Nice. For example, with numbers. So the same situation is here with numbers addition, right? We can sum two numbers, and we can produce a number also. So we are just replacing these boxes with some instances that we are caring about, and we have this operation in between that is combining these two types. And so this operation, I will switch to Scala code. So this is example of implementation in Cat's library for monoid. But before I say what is the monoid, this is this operation of combining two elements and producing the same element. So monoids is composed of two equations, of two functions. One is to combine, and this is part of the semigroup, and another is operation is empty, so monoid gives this empty function, but extending the semigroup. So monoid is usually presented with two operations: combine and empty, or append and empty, or zero, or append concatenation, or in more general way multiplication, right? And this is exactly how Greg presented here with multiplication. So Greg said this is the zero and this is the multiplication. But Greg also gives these generators. So we can have many different elements that are part of our monoid. For example, numbers. So what will be the numbers here? So let me go back. So this is one way of representing monoid for numbers. But what will happen if I write something like this? So this means we have, for numbers, we have two different monoids, right? Two different operations. So what will be the empty in this case? What will be the empty for strings as a monoid? What will be the empty for numbers with plus as a monoid? And what will be the empty if this is multiplication for numbers?
Empty string 0 for plus and 1 for multiplication.
Yeah, exactly. So how we choose, and this is this E, how Greg this represents. And all of these numbers are G, G, N, G. So from 1 to like infinity, right? So this is how monoid is like very simple structure with this basically one operation plus 0 plus this empty object. Does this make sense so far?
Yes.
Cool. And for example, in Haskell, there are two definitions for monoid, for numbers. So when you're doing some operation on numbers and you need instance for a monoid, you need to specify which monoid you want to use. Because if you remember from previous sessions, I was explaining how Scala is searching for implicit instances, and if we have two different implementations, we need to specify which one. And a similar situation is here for monoid, and this is the same situation in Haskell. When you need to say, oh, this is my product monoid or addition monoid. So, but now I want to show how monoid can be seen in general, like in the languages that we all write. So so for example, if we have some program and this program, we can say let's be, oh, I will not call this E. like expression. So it's this is a program parameterized with expression. So when we are writing our code, what do we really write? We really write these expressions combining with a semicolon. And maybe this is not always expression. Maybe we have a language like JavaScript where we have statements and, right, not only expressions. But basically, this is our language, right? So this is not completely obvious, because when we are writing our code, we are usually put this at the end, another semicolon, right? But we can ask, well, what is behind the semicolon? I mean, nothing, right? This is like end. So we can see as empty parentheses or these empty braces, right? So this is like an end. We have the sequence of our expressions, and at the end is the semicolon and like unit or nothing, zero. So if we have this zero here, then we can easily explain how is this at the end. So we can just keep this in mind and say, yeah, we know how to end with nothing, right? When we have some empty expression. So we can write programs and we can always finish with with nothing, right? We have this do nothing expression. So this is our, whoops. We can say, oh, come on. Oh. So this is our lambda calculus. So we can basically do the same thing, which can be more familiar to us because this is how Greg is presenting Rholang. So we can have our process, and I will say here, we don't know how this so that can be like a Rholang program, and we can have our process here, and we can say, yeah, to create a Rholang program, we combine these processes with our par operator. So now I must say this this line or this operator like or pipe, it's not the same as this one, right? This is this one is like meta operator of for definition of this monoid, and this one is operator that we have in our language, like a semicolon in lambda calculus. So do you see this connection between rho and lambda calculus?
Yes.
So this is basically monoid is everywhere, right? Wherever we can define this operation to combine things, we can define the monoid.
Mm.
And so now we can ask, what is the process, what is the expression, and how this works, right? But this is not directly connected to monoid structure. right? This is something connected to how this operation is implemented, right? Do you have some question or thoughts? Maybe another example of a monoid, or how do you see how this can be implemented in for example, like some language with lambda calculus, like JavaScript.
Those, there are two changes. You replaced expression by process, and then you replaced semicolon by a bar. So does it signify that you went from sequential to parallel computing or concurrent computing, or not?
Yeah, this is a good question, and I didn't mention how we will what will happen when this append or concat or combine operation is executed. So this is not what the monoid is telling us, but you pointed out important thing, and this is that there are some laws that monoid needs to obey, and this laws is what Greg shows here. Yeah, here. So any element with 0 is equal to this element, and this 0 can be on any side. So this is the first law, and the second is associativity, so that whenever we put parentheses, this will be equal. And this means we can first do our operation on these two elements and then combine the first, or we can first combine like these two elements and after that combine the latest one. So it doesn't matter. And so now we can think, yeah, what will happen in the what is difference between lambda calculus and raw calculus? And this is exactly what you said. Raw calculus says we can do this operation in parallel. Right? We can just execute whatever we have in this combined operator. We can just execute this in parallel, and we still have this. We are obeying this law. And in lambda calculus, we say no. This operation will happen in sequence. So we still have this associativity in a sense, but we need to execute this operation in sequence. And for example, when we are concatenating strings, this is like a list of characters. We can concatenate in any way we want, but and we will always get the same list. So this works with lambda calculus. But the another thing is how we will execute or what we are thinking about execution. What this means. This doesn't tell us from a monoid, right? So this is why Greg is saying there is a rewrite rule in addition to this monoid rule, which says how these processes, when they are in this monoid, how they will collapse. What will happen when we have a process which is sent and what will happen when we have received, and they are both in the on the same channel. And then this will happen. This operation of combining, this will happen. If we don't have send receive, nothing will happen. We will still have this par. It will stay in the state, and nothing will happen. But when some another sender receive that is matching what we on this what we have, we will have this rewrites. So this is like another. So we can say we have like special string monoid, but but if we have two characters that are the same in this string, we will just combine it into one, right? And so in that sense, we are creating some strange structure. It's not the set because you can have two elements that are the same, but if they are next to each other, we will just combine it. So in that way, we have some kind of simple execution. It's like a very simple language, but we have just a little bit of execution. We are saying, oh, two characters combining, there will be like combined into one. And this is basically like a very simple language, but Rholang is very powerful language, but also is using these very simple rules. This is really why it's powerful. And I wanted to mention what is the relation between lambda calculus and rho calculus. So
Tomislav, can you just tell me in the example, what is the, above it says input and output. So what's the operational semantics for the input and what's the logical output in the example?
In which example do you think?
The one you're looking at, the one that the cursor's at. It says example.
So here, here is not there is no operational semantics here.
Okay.
Because here we are not talking about rewrite rules.
Okay. Okay.
And so this is part of our structure. So I'm thinking. Yeah, it's here definitely we don't have operational semantics because operational semantics. Maybe I can say all of these things together are really operational semantics, as Greg mentioned here. So I'm struggling with exactly to say what these terms means because I'm not completely sure. Okay. Yeah, but this definitely doesn't say anything about rewrite rules. So when Greg explained to us in his lectures of introduction to the design of computational calculi, he made this distinction. This is the structure. How to combine things, and then in the different equations, he said this is the like rewrite rule, which is different from just combining things. Because in rewrite rules, we are forgetting things. As I mentioned, we have this. We can have this strange rule. If two characters are the same, we will just erase, one of them, and we will have one. So if we have multiple characters, we will erase all these characters, and we will have only one. So we basically forget what was the input. And this is like very similar how when Rholang is executed, we just forget what was the previous state. I mean, we are remembering everything in the blockchain, right? Because we want to have history. but from the perspective of execution, we really forget what was the previous state.
Okay, then in Scala, you showed us one example of the monoid, but was there an example with using applicative? That's library.
So applicative is in the different, like a different branch. It's not directly related to monoid structure.
Okay.
And what is also different, I have here this monoid K definition. This is almost the same as monoid, but it's more similar to applicative in a sense that it has this F parameter as a higher kind of type. So here monoid of F, and this F is not just just the type, but type constructor, if you remember for previous sessions. So it is a type that accepts another type. So applicative is like higher order in that sense, like this monoid K. So monoid is basically just defined as a normal type. It accepts a normal type parameter. And so here it's also, I mentioned this because Greg also make this distinction, right? Monoid is not parametric, and he exactly says, you know, how monad is really parametric in the, it has this additional type parameter that can be specified for this operation, for this plus operation, this combined operation.
So what's the difference between monoid K and monad?
Yeah, the type is almost the same. And the difference is that monoid K don't have this ability to somehow depend operation between these two, depend in arguments between these two elements. So this is not visible here, but NA can depend on the result of MA. That's the real difference. But just from the perspective of structure, we can see that they're almost the same, right?
Mm-hmm.
There is another, a monad gives this additional sequencing operation that can depend on previous result. That's the whole point of the monad.
Cool.
I don't have anything else to say about monoid.
Okay.
Yeah. So maybe I can just say for next time what I want to cover. So I don't just put
monad.
Sorry.
Talk about monad.
Yeah, I'm circling around, and you know, I'm talking about a little about monad, and then so yeah, I want to cover like different structures and you know what really monad is, and so I want to say this from the perspective of this semicolon, and you know how we can see. I think that Philip Adler said that a semicolon is like flat map for monad. Yeah, I want to go into details for that. So maybe I can just quickly say what I mean. So when we write our programs, like very standard JavaScript, where a equal 1, and then another variable b. Our execution is in sequence, right? We can also have if we have function plus, and we already know what is function plus, we can define our variable c, which is a plus b, and semicolon. And at the end, we can say, yeah, we have our unit if we are returning nothing. And from the perspective of monad, or a language that we have this monad, we would write this differently. We would say we need to package up everything inside something. So we will say a in pure. So we want to package up this in pure. So for B, we will do the same thing. And then we would package up this in the pure. So now I'm writing this in different style. This is not okay. Let's do the same. 1 plus 2. So this whole expression is then in our for. Right, and then, well, don't want to have this here because I don't want to write yield. So now we think about this as so this is a yield 1 plus 2. So in our sequential language, we don't see we don't see this monad out that we are working in, and here we are exactly see that we are inside something. We are inside this for, right? So we have this first expression, we have the second expression, and then we are returning something, and all of this will be in our monad. And basically, in our normal language, we are doing the same thing, but this monad is hidden, right? When the first expression is executed somewhere in the background, this is this A is remembered, and then B is remembered, and then to calculate C, this A is pulled from environment, and then B is pulled from environment, and then to be correct, we can return. So that oh, sorry for my pen is not very well. So when we this is return C. Sorry. So so for C, we are getting this A and B from environment. We are getting this function for environment, and we are returning the C. So we have the very much the same situation in both cases, right? But we don't see this monad. So this is why in Scala and other languages we have both of these syntax. For example, in Haskell, there is no distinction. There is only the only way to produce sequence operation is with monads. So this is the only way. And why we have confusion in Scala, for example, we have both. We have syntax for both ways, and this is confusing because they are part of different execution, right? Without monads, the execution is directly with Java, and when we are package up things in this monadic style, we have some another library that controls execution, like Monix or Cat's effects or Zio, as I mentioned in this article. So there is this desire to not write programs directly in execution of our runtime, because we want to have more control, right? And this is what this monadic style is giving us, like abstraction, so that we can use different execution environment. You know, one is better of the other, and you know. But basically, we are confined to write this in sequence, right? And yeah, I wanted to mention in the background, I said A and B will be pulled from the environment. And which environment? Where is this environment? So we have some kind of state. Our program in the background has some kind of state. And in sequential languages, this state is stored in the stack. So when we call this C, when we call A plus B, we are changing the stack. So we are saying, oh, we will now call this function, but this function, and we will put our current state that we have, we will put on the stack. So when this function will be executed, this plus function, we will return back, restore our state from the stack, and then continue. And in Rholang, we have a much greater expressibility, because we are not confined to stack. We have tuple space, and tuple space doesn't force us to have sequential execution. And this is why this is where this difference coming from. We can access the whole tuple space, right? So I wanted to show exactly that in more details, right? How we can have stacks in normal languages, and how now we have in Rholang we have tuple space, right? Which is like much more. We have much more freedom, right? We can use the whole state in however we want, and of course, but we don't want to use state in any way. We want to have like very good language with good way of specifying how the state can be modified, and that's the whole point. The language on top of this state is something that is preventing us to change the state in any way we want, so that nobody understands how this works, right? For example, in C, we have C language so that we can manipulate memory. Like memory is just a big state, like a tuple space. So we have some constrained way of changing this state, this large state. Is this make sense?
Yeah.
So I don't like too much different ways of defining what is like very basic operations, right? We can create many different words how to express this, but basically we have state, and we want to create only we want to change this state in very controlled way. So we want to say, yeah, we have this large memory in our machines, but we have this very nice language so that this memory will not be corrupted. One program will not change the memory of another program, and these kind of things. So this is what we will want. Or as Dan is talking about object capabilities, and this is basically the same thing. We are protecting this memory. So we want to have these object capabilities. We want to have this language that is exactly, that is like a layer on top of this state, so that when we express something in this language, we are completely sure how this state will change, right? Even if we have large programs, many programs running in parallel, we will always know how the state will change. And this is why Rholang is the next stage, because now we can write parallel programs from the beginning. We don't need different semaphores, mutex, or whatever to somehow, you know, write parallel programs, because we started from sequential. Right? We want to start from parallel and then just, you know, impose sequential when we want, right? And not the other way around. This is like super hard.
So would the pi calculus be sufficient here?
Yeah. And but with Rholang we have reflection, so we can inspect our programs directly in the same language and the same syntax that we are writing our programs. This is like something that, you know, we really want.
Yeah.
And we still, I think we still didn't really used this Rholang feature for reflection. It's like,
well, we use it in matching, but
yeah, but this will be especially important when we will have types, like behavior types, and on top of that, having reflection is like this, like almost sounds impossible, right?
Very good. Thank you, Tomislav.
Thanks. That was great.
I'm preparing a talk for our Lambda meetup in Zagreb. So I'm combining these small pieces and, you know, trying to present this in a way that is somehow understandable. So
Well, neat.
I want to practice. Yeah.
Well, yeah, you're working towards getting the credentials of Professor Grospick. You'll be going on a lecture tour, your mathematical lecture tour around the world. So yeah, but we're fortunate to have you now in the early days for you to share your wisdom. So we appreciate that. Thanks.
I want to have like a good introduction for existing developers from Lambda calculus and existing languages, to understand not only, you know, oh, this is like a new language, but from Greg's paper, Greg is explaining the structure of any language, right? Because with ladle or operational semantics in logical form, we can generate any type systems. So for me, it totally makes sense that, you know, we are presenting some kind of, we can explain all of the languages that we have now, right? I'm thinking like to have presentation, learn all the languages in half an hour, right?
Will you do your presentation in English or in Croatian?
Yeah, I'm thinking now to make it online, and yeah, maybe I would like to combine this group with a group that we have. So, you know.
No, but in which language will you do your presentation in Zagreb? in English?
Oh, previously I was on Croatian, but now I'm thinking on English. Yeah.
Okay.
And yeah, now I'm organizer of these two groups, Lambda meetup and RChain meetup. So I want to like combine Lambda to Rholang from these two groups, right? Like different presentations, but yeah.
Great. Wow. So good. And then, Tomislav, did you say that you're thinking of you have some ideas for next week's education session?
Yeah, I was thinking we can go into these boxes, right? Into proc and expression.
Okay.
So how this monoid is executing. So now we can add more structure. We can say, oh, in Lambda we have a different expression, if then else. You know, in Rholang we have send receives. So
Okay.
so we can like slowly move what Greg is explaining in the whole operational semantics. All of these rules and.
Okay, very good. Well, great. These Scala development sessions are tremendous. So we're really starting to build a body of educational material, I think, for people coming up from behind us in the future to learn from. So good. Well, we're getting close to the top of the hour. We've got another 5 minutes. Does anyone have any thoughts or questions? Okay. Well, good. Well, yeah. Once again, thank you, Tomislav. You know, we really appreciate you taking the effort to put together these presentations, and I think all of us are. It's very helpful in understanding very complex topics.
Yeah, and thanks for listening and questions. I mean, this is really valuable for me too, because I know that I'm you know maybe forgetting to explain something, and you know, so well I'm still trying to put all of the holes, you know.
And what's helpful is, you know, we kind of start the beginning of the week with the Casper stand-up, you know, with Greg's discussions on his research. And, you know, that's, some of us may get that, some of us may not, but we just have a sort of a general understanding. But, you know, coming into, you know, the education series, you kind of elaborate, you know, you start to explain what it is Greg was explaining and how it fits into, you know, the bigger picture, you know, the significance of it. So, you know, having that tie-in is very helpful. So putting everything in context. So they complement. You know, I think this education session helps complement the Casper stand-up, and by, you know, keeping up with both of those, you really, you know, you get a better understanding of, you know, what the larger effort is. And yeah, and that's, you know, it's I think we start to understand the scope and scale of you know, I mean, what we're a part of is really a big deal, and we, you know, we want to all working together to bring it to fruition, bring it into the world. But you know, this is big stuff. So, you know, it's kind of exciting that we're here in the early days, you know, putting it together. So, I mean, this is great.
So Thomas, I'm wondering if it would be meaningful to relate monoids to groups, rings.
Oh yeah. Yeah. So the group is a monoid with inverse operation.
With what?
So yeah, with inverse operation.
Ah.
So if we have a monoid with plus, so plus 0 monoid for numbers, and if we add the minus operation, we will have group. And there is one question that I have for that, you know, is this the same thing? Is this monoid with this additional operation completely the same? I mean, it is operationally the same. You don't see a difference. But I was listening different talks where this is not completely the same, because this is like a group has this inside the structure, and monoid with this additional operation is like, it's not completely the same. But I'm not sure why, but yeah.
The monoid can really only go one way, right? Whereas,
yeah, yes, and this is
bidirectional.
yeah, and you.
And how do we make a ring?
The ring, I think the ring is when we have two monoids that are touching in some way. Like.
All right. Well, I guess it's kind of late to get into that, but you know, I'm trying to dredge up from my memory stuff I used to understand about rings and fields, which are kind of very fuzzy at this point.
Yeah, I don't know too much. Yeah, also.
Okay, very good. Well, thank you, everyone. Thank you, Tomislav, for the presentation. So we'll look forward to seeing everyone back here next week and for another education session. So have a great week, everyone.
You too. Bye-bye.
Yep.